All right, so it says way back in geometry, you learned about similar triangles. With your neighbor, you're going to take a little bit of time here to brainstorm everything you remember about similar right triangles and write that information in the space below. Okay, so they have the same angles. And so we know that the side lengths do not have to be exactly the same, but there is a connection between the side lengths. And that connection, I'm going to say here that the sides are proportional. What that means is that the ratio of one side length to another, if it's the same position of the sides on both triangles, that ratio would always simplify down to the same thing. So it's kind of like what we saw on the very first day, where we had our three triangles with the different side lengths that were red, green, and blue. For some reason I was thinking orange, I couldn't get the color. So what we saw is that when we did the ratio of like the red side to the green side for all three of our triangles, that ratio all simplified down to be the same number. Those three triangles on the first day were similar triangles because they all had the same angles. So that's something that we're going to need to think about in order to work through our problems today. So for the rest of the page here, we're actually just going to look at number 2, part A together, and then I'm going to give you some time to finish out the questions on your own. So it says to find each of the following missing parts of the triangle. We're going to show our work or explain how we found the answer. So in part A, what is the length of side A? This is actually a little review to the skill that we did yesterday. So when we know one of our acute angle measures, acute angle just means one of the angles that's less than 90 degrees. We've got one angle measure, we've got one side length, and then we're trying to get the other side. This is where we can think about setting up a trig equation to solve for that missing side. So in labeling the pieces here, the side that we're looking for is the opposite side. We know the hypotenuse. And so we can think about using sine. We know that sine from SOHCAHTOA is equal to the opposite side over the hypotenuse. And so let's fill in our angle here. So the sine of 19.5 degrees is equal to A over 9. This is the easier version of solving this kind of trig equation because our variable is in the numerator. So all we have to do here is multiply both sides by 9. And then we can go to our calculator here. So I'm just going to type in 9 multiplied by the sine of 19.5. And this looks like it's very close to 3. In fact, I'm just going to round it to 3. There's a few decimal digits beyond it, but I'm going to say that it's essentially equal to 3. And I could also go back up and label that right here in the picture. Okay, so with that as a start, I'm going to give you some time to continue working through parts B, C, and D. So you are going to finish the rest of number 2, and then I want you to try all of number 3, part B. So there seems to be a special connection between the two triangles here in part A and part B. What do we notice about the side lengths? Side lengths are exactly the same. And so what would be the measure of this missing angle in part B? 19.5. Yeah, so not only these triangles are not just similar to one another, they're congruent. They are exactly the same triangle. All right, let's take a look at the next piece down here. So for part C, we now have a new scenario, so it's not the same triangle as what we had before. We have one angle, we have one side, we're just trying to find the other side. So it looks like this is the opposite side that we're looking for again. We know the hypotenuse. So this is going to be a good one to set up a sine equation. Again, thinking about what we did in the last lesson. So the sine of our angle is equal to W over 6. So this time we are going to multiply both sides by 6. That's I would get rid of that 6 in the denominator. And when we go over here to our calculator, we're going to do 6 multiplied by the sine of 19.5. And we're getting that this is equal to approximately 2. Now, by the way, if you are not getting the same answers as I am, have me come and help and check your calculator. You need to make sure that you're in degree mode. Mine shows me what mode I'm in by saying the word degree up here at the top, but otherwise there's something that we can click on to check. If you are in radian mode, you will be getting different answers for this, so make sure you check with me if that's you. All right, so let's go back to this triangle here. All right, so we ended up getting that missing side to be 2. And it looks like we have another connection now between the next triangle. So we should hopefully see that the sides are the same again. Now both the hypotenuse is 6 on both of them, the other leg is 2 for both of them. So what would be the measure of this angle? Still 19.5. Okay, now something that's a little interesting about the 2 sets of triangles that we've done so far is that we're now seeing an example of the side lengths being proportional. So the triangle in part A and B is similar to the triangle in part C and D, and that's because they have the same angle. They have that same angle there of 19.5. So notice that when we did the opposite side over the hypotenuse, up here, we ended up getting 3/9, or 3/9. So that's actually another way that we can write out the sine of that angle, 3/9. Well, 3/9 simplifies down to 1/3. When we take a look down here, and we think about writing out the sine of 19.5 based on these side lengths, we get 2/6. Well, 2/6 also simplifies down to 1/3. So they're simplifying down to be the same ratio. All right, let's take a look here at part 3. So now we're going to use this triangle off to the right to answer the following questions. So in part A, it says to write out the sine ratio for theta and write an equation showing it. Although we don't know the measure of theta yet, it's not given to us as a label, we can see that our opposite side is 5, our hypotenuse is 15. So opposite over hypotenuse is 5/15. What does that simplify down to? Still simplifies down to be 1/3. So what is the measure of this angle? 19.5. How do you know? Yeah, exactly. We're just kind of thinking about the question in the opposite way. So at the top here, we saw that the sine of 19.5 degrees equals 1/3. Down here, we saw that the sine of 19.5 simplifies down to 1/3. So now the question says, okay, the sine of what angle equals 1/3? Well, we've been doing that. We just did it twice. So the angle would have to be 19.5 degrees. So this idea here of working backwards, you know the answer of what the sine is supposed to equal. We're working backwards to figure out what the measure is of our angle. So there's actually going to be an easier, faster way to do this calculation, and it's called using an inverse sine. And here's how that looks. All right, so let's say that we know the sine of some angle is equal to 1/3, like we have in this problem. If we do the inverse sine of 1/3, that's going to equal the missing angle measure that we're looking for. So we talked a little bit about inverse functions at the very end of first semester. Remember that when we have an inverse, we have a little -1 symbol. It kind of looks like it's up in the position of an exponent. It's not an exponent. It's just a symbol to represent inverse. When we did inverse functions before, it was all about undoing things, undoing whatever the original function did. So if we do the sine inverse of our answer, working backwards, that's going to give us our angle measure. Now I want to show you here how to type this into your calculator. In your calculator, we're going to find the second key, and then we're going to press the sine key. And when you press second sine, you're going to see the sign with the little -1, the inverse symbol, show up. So let's go back over here to our calculator. This will work on a scientific calculator as well. Press second sine. So here I have sine inverse. And then I'm going to go ahead and type in my fraction as 1/3. You can type it in as 1 divided by 3. And notice how the answer is about 19.5 degrees. So this is how we work backwards. Now, if I wanted to check this, I could do the sine of my answer, and I could actually type it out to be a little bit more accurate. When I do the sine of the answer, notice how I'm getting the number that I started with. I'm getting the 1/3. That's 0.3333 repeating. Here it is, 1 divided by 3. So that's the answer that we're getting. All right, so really in my equation here, I could replace this with 19.5 degrees. That statement is related to this statement. So if the sine of 19.5 degrees is equal to 1/3, then the sine inverse of 1/3 is equal to 19.5 degrees. So knowing that trick about the inverse, knowing how to do that on your calculator, this is now going to be how we can solve for any missing angle in a triangle. We don't have to look at 5 other triangles to try to work up to it or lead up to it. And that is the faster way to get a missing angle. All right, so I'm going to divide my section here in half. So our first learning target, learning goal for today had to do with taking a closer look at similar triangles. And here's what we saw. If two triangles are similar, their sides are proportional, and the corresponding angles are the same. Corresponding angles means the angle that is labeled in the same relative position between the two triangles. Knowing about similar triangles, this allows us to figure out angles from side ratios. So side ratios meaning like the opposite side over the hypotenuse, that's a ratio. Or the opposite side over the adjacent side, that's a different type of ratio. All right, and then we also saw inverse trig functions. This is a shortcut. This is a fast way to solve for a missing angle. So we use them to find angle measures from sides, meaning you have some side lengths given to you, and we're trying to figure out what is the angle on the inside of the triangle. All right, so here was the example that we did today. So we said the sine of some angle is equal to 1/3. So wherever that angle is measured, 1 is representing the opposite side length. 3 could represent the hypotenuse side length, because we know sine is opposite over hypotenuse. We want to work backwards to get our angle. Now, I want to show you a new way of displaying this that gets at this idea of whatever we do to one side of our equation, we're going to do the same thing to the other side. So think about starting with sine theta equals 1/3. The thing that we are going to do to both sides is we are going to take the sine inverse of both sides. Now, an inverse function always undoes what the original function does to the original input. And so on this left-hand side, this sine inverse, that is going to undo or cancel out the sine, leaving us with just theta. So that's how we get this statement here, that our angle theta is just simply going to be the sine inverse of whatever that fraction was. In this case, it's 1/3. And then just a reminder, again, the calculator buttons that we're pushing to get sine inverse to show up is we're going to press the second key before we press the sine key. Now, this does not just work for sine. It works for cosine. You could do the cosine inverse to undo cosine. If your ratio is like an adjacent side over hypotenuse, you can also do tan inverse to undo tan if the ratio you have is like the opposite side over the adjacent side. So these work for all three, sine, cosine, and tan. 1 and 2. All right, so number 1, we wanted to find the measure of angle A. So that's going to be here in this lower left corner, so I put a star next to that. And when we take a look at the sides that are labeled, the ones that were given, the side length 7 is the adjacent side relative to where our star is. This would actually be the opposite side over here, and we're not needing to do anything with the opposite side. We don't know the side length of it, but that's what it would be. And then the 8.6, that's going to be our hypotenuse. So we do need to figure out, okay, are we using sine, are we using cosine, or are we using tan? So our shortcut of SOHCAHTOA, or that trick, that phrase, is going to be really valuable here. So since we have the adjacent side and the hypotenuse, it's going to be cosine. And so initially when we set up our equation, we're saying that the cosine of angle A equals 7 divided by 8.6. So that's the information that we get from the triangle. Then we're solving for an angle here, so we need to undo this cosine. The only thing that's going to undo the cosine is cosine inverse. And so essentially we're doing the cosine inverse of both sides. That's going to make the cosine to cancel out, leaving us with just A by itself. That is the only way to get rid of cosine. You can't divide by cosine. Cosine is not a number in and of itself. Cosine is a function. So you need to do the inverse of that function. Inverse is about undoing. On the other side, when we do cosine inverse of 7 divided by 8.6, we get 35.5 degrees. In our calculator here, we're just going to press second cosine, and then you can type in 7, type in the divide sign, 7 divided by 8.6, and that's how we're going to get our missing angle. Now, when we're solving for missing angles, I would like you to always put the degree symbol. Those are the units of your answer. So if you just have 35.5, yes, your calculation is correct, but let's add the degree symbol on there so we know, okay, we're talking about an angle. That's what we just found out. All right, let's take a look at number 2. So a triangle has a short leg that's 7 centimeters, a hypotenuse that's 13. We're going to draw a picture of the triangle, and we're going to find all the angle measures. So you can see the picture here drawn with that short leg of 7, the hypotenuse of 13. And I just started with this angle here in the lower left. You actually could do these in either order. You will still get the same answer at the end. But if we start here thinking about this as our start angle, right now, the way that it's pictured, the position of the 7 is the opposite side. The 13 is the hypotenuse. So we can say the sine of angle A equals 7 over 13. We're doing sine because of SOHCAHTOA. That's what we do for opposite and hypotenuse. And then we need to do the sine inverse. So sine inverse of both sides, that's going to give us our angle by itself. Sine inverse of 7/13 is about 32.6 degrees. Now the nice thing is that as soon as you know two angles, all you have to do is subtract them from 180 to get the third angle. The reason that it says 90 here, 90 subtracting the angle that we know, is because we already have an angle of 90 degrees. 180 minus 90 is 90. So that means A plus B together have to add up to 90. So that's going to give us our last answer that we're looking for. Angle B is 57.4. All right, so let's take a look at this scenario in the last problem. So it's giving us information again about this flight that happened back in 2009, and it says that the flight was flying by the George Washington Bridge at a height of 1,106 feet. From there, the plane landed safely in the Hudson River 6 miles away from the bridge. So this point right here is the bridge. The plane landed 6 miles away, so we're going to label that distance across the bottom as 6 miles. So here we have a picture that is modeling our scenario. At what angle was the plane descending? All right, so the angle that the plane was descending here. So if we take a look at the side lengths that were given, from where this angle here is positioned, so I'm going to think about putting a star right here. The 1106 is our opposite side. The 6 miles down here is the adjacent side. So if we think about SOHCAHTOA, what's going to relate opposite and adjacent now is tan. So we have the tan of our angle is equal to opposite over adjacent. Now, one thing we did have to do here is we need to get our units the same. So this 1106 is representing a measurement in feet. And then over here we have 6 miles. So if we go ahead and multiply 6 by 5280, how many feet we have in a mile, that's where we're getting those 31,680 feet. And when we do the tan inverse of both sides, we end up getting 2 degrees for our final answer. Now, if we take a look here at what's going on in the picture, you'll see that with the dotted line, we have a second triangle drawn that is equivalent to the first triangle. It's just kind of flipped over, and it's kind of making it look like it's a rectangle altogether. This little angle down here in that star corner is equivalent to this angle up here at the top, and this is the angle that we're looking for when it's asking for at what angle the plane is descending. But in the picture here, we can see that that little angle would be the same as the angle down there in the lower right.